Our last talk is Shoggoth, a formal foundation for strategic rewriting by Xueying.
Thank you. And okay, this is the last talk of today, and yeah, I'm not going to torture everyone. And yeah, here I'm going to present my work, Shoggoth, formal foundation for strategic rewriting, and this is joint work with all my collaborators, and especially Ohad and Michel are here, I think, yes. And we start with Shoggoth and strategic rewriting. So a Shoggoth is a blob with a lot of eyes, and it is a shapeshifter, and it makes a weird sound that no one can understand nowadays. And it's a monster created by H.P. Lovecraft. And strategic rewriting is a language performs syntactic transformation, and it lack of formal understanding. So that's why I named my project Shoggoth. Nothing to do with my mental status. And yes, overview of the strategic rewriting languages. And the core language we study is System S, which is created by previous authors. And it is adapted to a lot of strategic rewriting languages like Elevate for program optimization and Stratego and Stravinsky and Loud. And the basic constructions of these System S, these strategic languages are atomic strategies, which are like a single rewrite rule. For example, addition, commutativity of addition, or like commutativity of multiplication. And also there are composed strategies, which are composed by strategy combinators like sequential composition, left choice, and such. And they are important because they provide programmers, combinators, and generic traversals, allow them to control the application of the rewrite rules, and also allow them to reuse rewrite rules. And also there are a lot of application areas like program optimization and writing interpreters and compilers for DSLs. And then we moved on to, and it is important to understand, have a formal understanding of these strategic rewriting languages, because they can go wrong. They can result in errors, or they might not terminate, and they also they might not rewrite an expression into a desired form. And there are some existing formal works. For example, there are already existing big step operational semantics for System S, but without modeling divergence. And also there's existing sketches of Wikis precondition calculus for System S, making use of CTL, but it's not expressive enough to reason about nondeterminism in traversals, and it has some problems in fixed point operator constructions, and the soundness is not proven. So our contribution is we provide denotational and operational models for System S featuring non-determinism, errors, and divergence. Especially we have angelic non-determinism for errors and demonic non-determinism for divergence. And we prove these two models are equivalent. And we provide Wikis precondition calculus for these for strategic rewriting languages, and we demonstrate how to use this WP calculus to prove properties of strategic rewriting. And we start with syntax. And the expressions we are studying takes a very abstract form of an AST. It can be either a leaf or a node. And the syntax there are some simple strategies. It can be either skip, abort, or atomic strategy, and the variable is used in defining fixed point operator. And there are strategy combinators, can be sequential composition, or left choice, or non-deterministic choice. And there are also traversals, for example, one, some, and all. And all traversals are non-deterministic. And we start, and then we introduce the semantics for System S. We start with the simple ones. For example, the atomic strategy, skip, and abort, the operational model is very straightforward. And to define the denotational semantics, the execution of a strategy, it takes in a semantic environment which contains mappings from variables to domains, and our domain is pointwise lifted from an plotting power domain, which is the non-empty set or non-empty power set of all possible outcomes of a rewrite. It can be an expression, error, or divergence. Divergence is important. Consider sequential composition. If one part, the first strategy is divergence, or the second strategy divergence, the whole sequential composition will diverge. In the previous operational semantics, they didn't consider divergence. We extended to by co-induction to express divergence. So here's an example of the sequential composition. So the operational model, it can be either successfully executed if both S1 and S2 leads to successful execution, or it can go wrong if either of them goes wrong, or divergence or diverge. And the denotational semantics, it's more concise, and it basically expresses the same thing. We also need a fixed point operator because we have repeat, which means keep applying a strategy until it's no longer applicable. And we also have traversals like top-down, find the first possible position to apply a strategy. So that's why we need a fixed point operator to express these strategies. To provide a fixed point operator, we need to make sure that the fixed point is indeed the least fixed point. Therefore, we need to define this ordering of our domain. And this is basically our domain is a plotting power domain, and ordering is an algorithm ordering. And because our domain is a site, we can simplify this ordering by providing a POPL'24 ordering. Basically, this ordering holds if a set A is equals to set B, or the bottom in this case is singleton set of divergence is or divergence is in the set A, and excluding set A excluding the divergence will be a subset of set B. We find this POPL'24 ordering can be simpler for us to when we construct proofs. And this is a POPL'24 from 2500 BC. And yes, it is very important. It helps you to define your fixed point. And now we provide the semantics of the fixed point operator. We can provide the semantics of the fixed point operator. And again, we have the operational model and also the denotational model. And we prove our denotational and operational semantics are equivalent by the computational soundness and also computational adequacy. And all the proofs are mechanized by Isabel Hall. And then we move on to the location-based Wickes precondition calculus. Again, strategies can go wrong. They may result in error, and they may diverge, and maybe they result in undesired result. And the key observations are bad strategies can never lead to any successful execution, and good strategy may be unsuccessfully executed on some input. And to reason about execution of strategies, and also to characterize good and bad strategies, we introduce the Wickes precondition calculus. And this is a simple definition of the Wickes precondition calculus, which is standard. And in our case, the challenge is traversal because we do have the traversal operators to traverse the syntax tree. Therefore, we need a notion of location in our calculus. And therefore, we modify or we provide the weakest must succeed precondition, including the notion of location. So here, the zeta is the logic environment, and L is the notion of location, and P is a postcondition. By this, we can calculate the weakest precondition. And also, we have the weakest May error precondition, which is used to define the weakest must succeed precondition. This is a problem of my naming of my calculus. It's not very easy to pronounce. And then we can check if a strategy is well composed. For example, we have the sequential composition of commutativity of addition and commutativity of multiplication. We want to see if this is a bad strategy, and we can make use of the weakest precondition for atomic strategies, and then we can make use of the weakest precondition calculus for sequential compositions. And then by plug them in together, we can conclude that the weakest precondition of this sequential composition is an empty set. It means there's no expression can be successfully executed by this strategy. Therefore, this sequential composition is a bad strategy. And also, we can check if a strategy diverges. For example, repeat skip. Is this a bad strategy? And making use of the weakest precondition calculus for fixed point operators, and we can instantiate to define the weakest precondition for repeat. And again, the weakest precondition is an empty set, means there's no expression can be successfully executed by repeat skip. We can then conclude that this is indeed a bad strategy. And now we can characterize good and bad strategies, successful and unsuccessful executions based on our weakest precondition calculus. The good strategies are the ones for a given postcondition is not an empty set, and bad strategies for a given postcondition is an empty set. And the weakest precondition is an empty set. And also successful and for a successful execution, the expression input expression is indeed in the weakest precondition set, and also we can define unsuccessful execution similarly. And we also prove the soundness of our weakest precondition calculus with respect to the denotation of semantics. It means our weakest precondition calculus is indeed modeling successful executions as what we want according to our formal semantics. And all the proofs are mechanized and can be found on my GitHub. Conclusion. In our paper, we feature the formal semantics of system S. There are a lot of things I haven't introduced in this talk. And also we have the equivalence proofs for the semantics are in the paper. And also there's formalized weakest precondition calculus and soundness proof and more case studies demonstrating the usage of the weakest precondition calculus. And also our formal mechanized proofs are a part of the artifact. And future works, maybe we are considering maybe it can be used in reasoning or expressing or reasoning about graph rewrites, because currently we are only considering the rewriting on the tree, and maybe this can be used for the weakest precondition calculus can be used for automatic reasoning of the execution of strategies. And we are open to more suggestions of future works and open research questions. And that's the end. Thank you.
Thank you for an interesting talk. So you mentioned something about like the use of both angelic and de Moivre determinism regarding the divergence and error. And can you elaborate more on that? And can you also elaborate more on how does that affect the weakest precondition calculus?
Well, I can definitely elaborate more on that. So for example, we have the non-deterministic choice. It has strategy 1 and strategy 2. And so for angelic non-determinism, of the treatment of error is if one of them goes wrong, we still consider there's a path for successful execution. And for the demonic treatment, non-determinism treatment for divergence, we say it will only be successfully executed if neither of these two strategies diverges. Because we think errors are okay-ish, but divergence are harder to recover. So that's why we choose this kind of treatment of different treatment for non-determinism. Yes.
And your meaning of the weakest precondition captures that, like, if it can successfully execute without divergence and error at the same time, right?
Of course, no. It won't. It won't successfully execute it or error at the same time. Yes. So the weakest must succeed precondition captures it must succeed, as the may error precondition captures it may be succeed and may error.
I see. Thank you.
Welcome.
Any more questions? Oh yeah.
Thanks for the talk. I was just wondering, because you say in future works, an idea is to apply it to sort of analysis or bug finding, I guess. I'm just wondering do you know if programmers who are writing programs in these strategic rewriting languages, is it a particular problem for them? Do they easily write programs which represent bad strategies, for example? Or,
Well,
I mean, I have no feeling about this. I'm just really asking for interest here.
well, so for optimization, certainly there are programs like easy goes wrong, and yes, so yes, there are problems.
Could you give maybe a quick example?
Okay, Michel, can you give an example for what goes wrong in Advice?
So we have a paper at ICFP 2020 where we use these rewrite languages to express real compiler optimizations. And the longest kind of trace of successful rewrite execution requires 50,000 rewrite steps. So writing programs that kind of perform that long rewrite sequences are fairly complicated. And it required quite a bit of effort to get them correct. So this is actually helpful in writing such complicated strategies.
Thank you, and thank you.
Any more questions? A quick one. One quick one.
Do you think there is a room for like extending the system S in any way? Like, for instance, if a strategy computes some value and then passes the value to the later strategy or something like that?
Isn't that what sequential composition does? So the first strategy computes to some value.
But it's not passing the value to the later strategy. It's just a sequential composition without passing the value.
Without passing the value. Can you elaborate on that?
We can take it further offline.
Okay, sure. Okay, thank you.
Is there no more questions? We can wrap up there. Well, thank you very much, and thanks to all the student volunteers as well.
Thank you.